Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everybody. Happy Monday. How's everybody doing today?
Anxious.
Anxious about the
Yeah, for the midterm.
Oh, yeah, that's understandable. I mean, it's it's our first kind of first time I've actually done or administered a take-home midterm. So, yeah, I think definitely there'll be an experience for all of us. So, you guys are my guinea pigs, kind of as you usually are. Believe it or not, even though it's this late in the evening on a Monday, you guys are actually the first class that I see in the week, because I'm teaching all electives and grad classes this semester. So all my classes are late in the evening. So you guys will be my guinea pigs. So you guys will have to let me know how it goes. But I made the exam last week and I took it at the end of last week. And it wasn't too bad, which is easy for me to say because I wrote the exam. But it's very consistent with what's on the homeworks. Most of the problem 2s and the problem 1s. So hopefully we'll be okay. But let's talk today a little bit about the kind of what to kind of expect and how you can ask questions and stuff like that, because I think that's going to be important. Okay. Okay. So let's go ahead and jump into it. Oops. All right. So I'm trying out something new on my iPad right now. So I have a new app right now. So hopefully this will make my writing a little bit neater, because this is the app that's supposed to come with my stylus, so I can actually rest my palm on my iPad, so I can actually write a little bit neater this way. So hopefully that's nicer. Okay. I know there's some questions on homework 5, so I want to do an example of the corner cell, which I think a lot of people had questions on that. And then besides that, first let's actually just talk about the midterm. So the midterm is going to be this Wednesday. So just like we talked about before, it's you guys are going to have 24 hours to do it. So what's going to happen is at 5:30 p.m. on Wednesday, what I'm going to do is I'm going to upload the exam, basically as like an assignment that you'll see on Titanium. And then from there, you can download the PDF of the exam. And then you're going to have 24 hours to finish it, and then to upload it back to upload your answers back to Titanium at 5:30 the next day. So I made the exam basically in the same format as before, basically as if I was giving it in the class. So if you have a printer at your house, you're certainly welcome to print it out and write directly on there. If you don't want to print it out, if you want to use your own paper, that's fine with me too. Just if you're going to use your own paper, just please write down the question that you're going to answer and give me some heading, just so I kind of know which answers which, and it's a bit easier to follow. But either way is okay. So if you don't have a printer, then that's just kind of use just whatever line paper you have available to you. Of course, since it's a take-home exam, you'll have all your notes and you'll have the lecture notes and the lecture videos that will be available to you. So you can definitely make use of that. And then if you have questions on the exam, so I'm not going to open up the lecture Zoom meeting next Wednesday. Or this upcoming Wednesday for the exam. So if you have questions on the exam, just send me an email and then I'll get back to you as soon as I can. So I won't open up the Zoom lecture room, but I will be basically sitting at my laptop, basically waiting to answer any questions. So so please just email me your questions and I'd be happy to answer from there. Okay. Okay. Are there any questions on the exam format and kind of just the expectations on the exam?
For the exam, would we just take a picture and then send it as a PDF, like the same way we've been doing it for the homework?
Yeah. If you can take pictures with your phone and then convert it to PDF, I think that would work the best for me, just so it's all in one, file. Because sometimes with people, they just take the pictures and then they upload just the JPEGs. So if that's all your phone can do, that's fine with me too. But for me, it's a bit more convenient when it's all kind of in one file and I can just scroll down and see your answers. So a question from the chat is, am I grading more strictly because we have more time? No. So the exam is basically going to be the same as if we had it in the class. So the questions are I didn't change the questions at all, and I'm going to grade it basically the exact same way. So of course, because the exam is take home and you'll have all your notes and lecture material available to you. Definitely, I expect the scores to be a bit higher. So I did get a couple questions, about the, the grading, just in terms of, am I going to grade more strict, and how's that going to affect the grade? So, for me, my grading policy is I don't grade on a curve on purpose, just because I think it's a bit unfair to kind of, I think what some faculty, they kind of pre-decide how many people should get A's and B's and whatever. And I think that's kind of unfair. So, what I'm going to do is basically just grade everything just kind of straight up. So, I expect the grades to be a bit higher than normal, but I think, given the circumstance, like I think that's perfectly okay. And, at the end of the day, this is an elective too, where, all you guys are here because, you want to learn something that's, going to be valuable, hopefully, for you and your career. So, the grade is a bit less important, and it's certainly less important than like a lot of the real life stuff that you guys are dealing with right now too. So I don't want you guys to stress about that. I just want you to just kind of do your best and kind of just take the class kind of as if, we were still in, in regular session, and I'll kind of grade it exactly the same way. Okay. Okay. Any other questions on the exams or grading before we go over the previous homework, or just one of the problems?
Professor, how long will the exam take? Is it exactly like our other tests? It would be like an hour and a half.
So I wrote it as if, it would take the exact same time. When I took it, it took me like a bit over 30 minutes, but I was eating like ice cream and a bag of chips while I was writing the solution. So it's a bit hard, because usually when I do my own solutions, I take it kind of in an intense test taking environment where I kind of time myself and I don't do anything else. But this time I was kind of leisurely taking it in my apartment. So it took me a bit over half an hour, just because I was eating snacks while I was doing it. But I expect it's roughly, it's about the same length as the other exam. But don't put it off for the last hour 15. Definitely make use of the full 24 hours if you can. Mm-hmm.
Professor, quick question. Can you hear me?
Yeah. Mm-hmm.
Just on the study guide, you mentioned the MATLAB. Is there going to be any MATLAB coding on the exam?
No. Yeah. So the exam is basically going to be the exact same format as the first exam. So it's just going to be, you're just going to be writing out the equations basically and answering conceptual questions. So there's no MATLAB on the exam.
Gotcha. Thank you.
Mm-hmm. What flavor? I was eating barbecue Lays.
Yeah, oh, is it trick to eat chips and ice cream and we get a good score? A good concentration?
That I cannot say. If it helps you concentrate, then I would say go for it. But just don't get spill ice cream on the exam, just so I can still read it. Yeah.
For the last homework, for the what does it mean by linear something on as homework question?
Sure. Yeah, we can go over that really quick.
What's a linear variation?
Yeah. Yeah. So so you're talking about kind of finite volumes. So remember, finite volumes. What happens often is that you have kind of let's just take a 1D case, and we have a cell that's given by this, right? So we have our cell-centered value phi c here, and then in the neighboring cell, we have, say, the cell-centered value is phi r. Okay. But what comes out of our finite volume approximations a lot of time is we have to evaluate the values here. Okay. So in particular for diffusion, for this case, we have to evaluate the derivative, right? So we have to evaluate d phi dx at xr, okay? So what I mean by linear variation is that we basically are assuming that the solution varies linearly in between phi c and phi r. Okay. And so what that means is that, you know, when we approximate this derivative, you know, ultimately what we say is that this derivative is going to be the slope of the line between phi c and phi r. So if we say that phi c is something like this, and we say that phi r is something like that, okay, and we draw a line in between them, then what we say is that the slope of this line is going to be equal to phi r minus phi sub c divided by delta x. Okay. So basically by assuming that the variation between those is linear, then we get the slope by that expression right there.
Oh, so it means we're using a slope linearly to assume the value between those two.
Exactly. Yep.
Okay, that makes sense. Okay, thank you.
Mm-hmm. Okay. So, and then I know there's a question on problem 2b, so particularly for the corner cells, right?
Professor, I also have a question for problem 2b, but it's on regards to something else other than the corner cells.
Okay, yeah, let's do corner cell 1, and then I'll answer your question after that. Okay. So then the corner cell 1 was this guy in the corner right here. So then I think the relevant boundary conditions are the ones that border it. So we have d phi dn is equal to minus 10. So we have a Neumann condition on the left. And then on the south side, we have a Dirichlet condition of 45. Okay. So basically what we need to do is we want to find the FVM equation for this guy. So usually, you know, with these 2D problems, and you have with finite volumes, and you have kind of differing boundary conditions on either sides, I think the best way to go about this, and I'll admit when I made these solutions, I didn't do this, but I think the best way to go about this is to basically write out the expressions for each of the 4 integrals. Okay. That's my cat. Okay. Because remember, when we do finite volumes in 2D, we're going to have an integral on each side of the cell. So we have an integral on the north side, an integral on the west side, integral on the south, and integral on the east. Okay. So in this particular case, you know, when we have 2 boundary conditions, we're going to replace 2 of these integrals with the boundary conditions. Okay. So we're going to replace first one we're going to replace is the west integral. So we're going to replace integral w. Okay. So we're going to replace this with the Neumann condition. Okay. And then we're going to replace integral south with the Dirichlet. Okay. Okay. So let's do the west integral first. So the west integral is d phi dx minus sine dy, right? So then when we evaluate this with the trapezoidal rule, this becomes minus d phi dx evaluated at the west face dy. Okay. Oh, sorry. And then we'll replace this with delta y here. Okay. Right. So then we need to replace this guy with the boundary condition. So the boundary condition that we have was that d phi dx was going to be a minus 10 there. So then we're going to have minus 10 times delta y. Okay. Okay. And then we have the south integral, where we're going to replace it with the Dirichlet boundary condition. Okay. So we have d phi dy minus d phi dy dx, and that's going to be equal to minus d phi dy, evaluate at the south face, delta x, okay? So then if we evaluate this using the Dirichlet boundary condition, we get minus phi c minus phi naught divided by delta y divided by 2 delta x, okay? And then this is going to give us minus 2 phi c. And normally we assume that delta x and delta y are the same, so we can cancel those out, okay? Plus 2 phi naught, okay? Where this phi naught, we're going to move to the right-hand side. Okay. Okay, so then, so what we've done for the corner cell, since we're bordering two boundary conditions, is we've replaced two of those integrals with expressions that have the boundary. Okay. All right, any questions on this? Okay. So let's put it together with the rest of the terms. Okay. So we replaced the west integral and the south integral, but the north and the east integral are still going to be the same. Okay. Okay, so let's do the phi north first. So there's going to be d phi dy delta x. Okay. And then since we have a neighbor to the north, we can go ahead and do that. So the neighbor to the north is going to be 5. So we have phi 5 minus phi 1 all over delta y times delta x. Okay. So this is going to cancel out. And then we have phi to the east, which is d phi dx dy is equal to d phi dx at the east face, delta y, okay? So then our neighbor to the east is phi 2, so we have phi 2 minus phi 1 divided by delta x times delta y, okay? And those are going to cancel out, okay? So now that we have our 4 integrals, let's add them all together, okay? Okay. So first we have phi, let's add phi to the north. So we have phi 5 minus phi 1, okay, plus phi to the east. So that's phi 2 minus phi 1, okay. And then let's subtract our phi to the west, which was, or let's add that. Right, so phi to the west was a positive 10 delta x. Okay. And then let's add our phi to the south, which was minus 2 phi c plus 2 phi naught, where phi naught is 45. Okay. And then let's see, we had a k value of 5. Okay, so all this is going to be multiplied by minus 5. And this is going to be equal to q of xc. Okay. So then basically what you can do is you can simplify this and basically move all the terms around. And then you should get the right answer. So let's go ahead and evaluate that. So let's see, we have a delta x of 0.25. Okay, I see the mistake now, because I think in my solutions I forgot this 2 right here. Yes. Right, so Mario, you said you got 102.5 on that side, right?
So I corrected my math, and I got, let me see my calculator. I got a positive 92.5.
Positive 92.5.
Yeah, so I got opposite of what you wrote in the solution.
Okay, I see. But your coefficients on the left-hand side are the same as mine. So you have a positive 1 in front of phi 5, a positive 1 in front of phi 2, and a negative 4 in front of phi 1. Is that correct?
Correct.
Okay. All right. Let's work through this then. Okay. So then we divide by -5 because that's what we usually do. Okay.
Professor, it's not going to be the opposite sign of k?
Well, the original equation had a -k out in front, so the k is 5 in this case because we had -5 in the problem.
That's what I'm saying. Is that it's not supposed to be positive, or like, are we switching the sign on it or not? Or
No, because the original equation had -5 out in front of it, so then we had kind of so then k has to be 5 basically in order to satisfy that.
but you're multiplying it by -5.
Yeah. So the -5, I'm multiplying by -k. Sorry.
Which would make it positive.
No, because k is 5.
K is equal to 5.
Yeah, and then we multiply by -k because eventually we usually divide by -k, so we have q of xc divided by -k.
Okay. All right.
Yeah. No, I forgot the delta squared next to q of xc.
Wait, so we wouldn't use the formula -k times the value of east plus north plus west plus south minus 4 c?
That's only for an inner node or inner cell. Sorry, because for an inner cell you have neighbors on the north, south, east, and west side. But since this is a boundary, we only have neighbors to the east and to the north. So you need to replace the west and the south integrals by the boundary conditions.
Yeah, because I thought like for the boundary ones, you just move those over to the right side.
Yeah,
since you're replacing them.
Yeah, we will. Yeah, we're gonna move those over to the right side. Yeah. So the question from the chat is, in the notes there are rule shortcuts for dealing with modifying the equations. In the tests, you have to do such integrals. For diffusion, those shortcuts should work pretty well. The only one you have to be careful of is the Neumann condition. I think I was I think I jumped the gun a little bit on the Neumann condition. So if you have a Neumann condition on the exam, I would work it through from the integral just to make sure you have the correct sign, because yeah, the signs can be quite tricky in this one. But the rules from the notes should work for Dirichlet boundary conditions. Yeah. Okay. So Mario, I think I just kind of did it in my head again. I think it should be yeah, it should still be okay, or it should still be in -92 because you have a positive 2 phi naught right here, where phi naught is 45. So when you subtract to the other side, you should get -90, and then this becomes a -2.5 right here.
Okay.
Yeah.
I'll check my sign values to see where I got confused.
Yeah, so make sure when you're doing the integrals on the west and the south side, make sure that there's a negative in front of those integrals. I think that's probably where the issue is.
Oh, okay.
Yeah.
Thank you.
Yeah. Yeah, these corner cells are definitely tricky because you have to apply kind of 2 boundary conditions. So when you're not sure, working it through from the integrals, I think it's probably the safest bet for this guy.
Professor, just to be clear, for the exam, you do not want us to use the shortcuts, or?
So you can use the shortcuts for the Dirichlet boundary condition, because I know those will work. The signs will work well for that. But for the Neumann conditions, I would work it through from the integrals.
Even though you gave us the north and east is positive and south and west is negative?
Yeah.
Because you still divide by the k and negative k, and it changes the value. That's what I did for this question, and it worked out.
Oh, okay. Yeah, I think for this one it probably worked out, but yeah, for the exam I would do it just do it from the integrals just to be safe.
Okay.
Yeah. Yeah, because when you do convection, you're definitely going to need to work it through on the integral, because for convection there's not any good rules for it. So it's definitely good practice to do.
Okay, thank you.
All right, and then Rick, you had another question on this problem too.
Yeah, I guess it's just a mixture of shortcuts and integrals.
Okay.
Because I guess for the Neumann condition, you do mention, for northeast it's going to be positive, and then for west south it's going to be negative. So
Yeah.
I boxed in an equation that you had for the Newman condition, and it was phi east plus phi west plus phi south minus 3 phi c equal to your equation q xr y and yc divided by delta squared plus k gamma delta. That's the equation I took from the notes. And then you said we're going to change that value on the right, the k gamma alpha, either positive or negative, depending on the sign on the side of.
Yeah, I think there's a typo in the notes where I think there shouldn't be a k on that one at least, and I think the signs on that one was wrong on that too. So I think Alfredo pointed that out over the weekend. So maybe I'll correct the notes, and I think I'll probably send a revised version because I think that was confusing some people too.
So just to clarify, you're saying for 2D diffusion, the Newman condition, you recommend going through the whole integral process rather than having some shortcut.
Yeah, I would recommend doing the integral process, especially because I think there's a typo or two in the notes. That I'll correct it and I'll get it up by tomorrow.
Okay. Are you last question? Are you going to be posting a solution for the homework with kind of like the okay, and it'll kind of go over like the little integral process, or will it be?
So in the homeworks, because there were a lot of equations, I did do the shortcuts on the homework. I think for this one it worked out, but yeah, I would use the process that's in the lecture notes to go through the integral on these ones. But I have solutions that are prepared, so I definitely want to get those out to you. So I'll have those out to you by tonight, and I'll have corrected lecture notes probably by tomorrow because I need a little bit of time to correct that.
Okay, that helps. Thank you.
Yeah. All right. Any more questions on this homework?
I had a quick question about the K values.
Okay.
Because there was a discrepancy with the sign values. So in the original equation that you give us, is it, so it says negative K. That means if we're given that like in front it says -6, so then it should be just 6 then?
Yeah.
It says negative?
Yeah. In the original equation, we have minus k times d squared phi dx squared plus d squared phi dy squared, right? So if you in a problem you get like you said like -6, d squared phi dx squared plus d squared phi dy squared. So in this case, k is 6. Yeah.
Okay, thank you. I was just so confused with that.
Yeah, it's confusing. So yeah, the reason I do that is because normally the diffusion term is on the same side of the equation as the source term. If you're kind of equating this to the heat equation or like the Navier-Stokes equations. So that's why I kind of moved it to the left. But when you move it to the left, then there's a negative out in front like that. So that's just to keep it consistent. Because normally, when you're doing physical problems, your parameters like these, like your diffusion coefficient, like your thermal conductivity or your viscosity, those are always positive values. So most time you don't have negative things. So I wanted to show you kind of the equations in the kind of its natural form so that you'd have all positive coefficients basically.
Also, is there going to be any convection on the test or no?
No.
Oh, okay.
Yeah, so the exam is going to be unsteady problems. So that's explicit Euler, implicit Euler, and then diffusion with FVM. So just this. So the stuff we're doing with convection that we started last time, we're going to continue today is not going to be on the exam.
Professor, I had a quick question about this problem.
Sure.
That -180 on the solution side, is that from the same formula that we used for the 1D case, which was, I believe, -k over delta x squared?
Which one are you referring to?
The -180 on the solution.
For which problem? 2b?
The same, yeah, the same problem, 2b.
Oh, you mean the -1/80?
Yes.
Yeah, so that's a result of k times delta squared, where I think delta in this case, or minus, it should be, sorry, it's delta squared over minus k, right? So delta in this case is 0.25. So if we have 1/4 squared times minus 1 over minus 5. Then you get 1 over 16 times minus 1 over 5, and you get minus 1 over 80. Yeah.
I got you. Thank you.
Mm-hmm. All right. Any last questions on this homework? Okay. So that's the homework. So I'll post the solutions that I have tonight, kind of after I give my second lecture, just so you guys will have it, because I know the exam is on Wednesday. And then tomorrow I'll go over my lecture notes, and I'll make sure I correct at least that typo, and then make sure you guys have that available for you too for the exam. Okay. Okay. So then let's continue where we left off with convection with FVM. Okay. So I think last time we were doing 1D problems. So our 1D problems look something like this. So we have d dx of u, which is our convection velocity, times phi minus k d dx of d phi dx is equal to q of x. Okay. So remember, the reason we put it in this form is so that when we take the integral of this, then both those terms can basically be easily evaluated. Okay. Okay. And then after we take the integral, we do our our several rules. So the in 1D we don't have to use divergence theorem, but here we have to use trapezoidal rule. So the only one we have to do it for is for the q of x on the x side. Okay. And then if we use kind of a standard kind of central scheme, which is what we usually do, we end up with this formula right here. Okay. So we get minus u divided by 2 minus k over delta x times phi L plus 2k over delta x phi sub c plus u over 2 minus k over delta x phi sub r is equal to q at xc times delta x. Okay. So this is our formula for an interior cell. Okay. So you know it's a formula for an interior cell because we have neighbors on the left and the right. Okay. So obviously you can't apply this if you have if your cell borders a boundary. So if you're on cell, the first cell in the grid or the very last one, because you have to have the boundary conditions. Okay. And with the boundary conditions, the best thing to do is for problems with convection and diffusion is to kind of work it through from the integral. Okay. So just to kind of sum it up really quick, so let's do a Dirichlet boundary condition. Okay.
Professor, could you go back really quick?
Sure.
Speaking for a classmate.
Oh, okay. Oh, sorry. Yeah. So the nice thing about this new app is that I can turn pages. So I'm gonna go a bit faster. So if there's ever time where I turn the page too quick, definitely let me know. I think it's I can always go back. So I think what I can do with these two is I can save this as like as a picture or as a PDF, and I can upload that to Titanium. Would that be helpful for you guys to have as well?
Yeah.
Okay. Okay. So let me do that too. So I'll after the lectures I'll save whatever I have notes here, and then I'll upload that on Titanium as well. Okay.
Professor, this is where we left off last lecture?
Yeah, this is where we left off last. So I'm just kind of recapping kind of what we did last lecture.
I don't know why, but I have a minus u over 2 plus k over delta x. And then at the right side, I have a minus gamma, or...
That's for the Neumann condition. So so what I have right now, this is just for the interior cells.
Okay.
Yeah, and then we're going to get to the ones with the boundary conditions next.
Oh, interior cells only. Ooh, make sure.
Okay. So if we have a, let's say we have a Dirichlet boundary condition on the left. Okay. So we have something like this. Okay. And then our cell is like this. Okay. So the formula that we got for that after applying the you know, our rules was like this. So we have u over 2 plus 3k over delta x times phi sub c plus u over 2 minus k over delta x times phi sub r is equal to q of xc delta x plus u phi naught plus 2k phi naught over delta x. Okay. So you notice here on the right-hand side, we basically have two terms that come out of the Dirichlet boundary condition because we have both convection and diffusion. Okay. Okay. So that's why for the cases with you know, both convection and diffusion, you know, it's good to go from the integral. So when we do the example, I'll do that. But for now, I'm just kind of recapping kind of what we did last time. Okay. Okay. So that was our Dirichlet boundary condition. And then let's say that we have a Neumann condition on the right. Oh, sorry. Was everyone done with this one right here? Okay. So we have a Neumann condition on the right. Where remember we're changing our definition of the Neumann condition slightly here just to make the computations easier. So Neumann condition, normally we use that to define the derivative of the solution at the boundary. Now what we're going to say is Neumann conditions, they define the total flux at the boundary. Okay. So I think for this one, it would be good to kind of go from the integral expression. Okay. So after we apply trapezoidal rule, we get something that looks like this. Okay, so we have, and I've kind of rearranged the terms, so I separated between terms on the right and terms on the left. Okay, so you have a u phi at xr minus k d phi dx at xr. Okay, so those are the terms that are valued on the right, minus u phi at xl minus k d phi dx at xl. So that's the total flux on the left side. So both our convection and our diffusive flux. Okay? And this is equal to q at xc times delta x. Okay. And so when I say that we're doing this as total flux, I'm going to draw the diagram here. So when I say that we're replacing or we're saying a Neumann condition is the total flux that's on the right side is both our diffusion and our convection term. Okay. So this entire expression here we're going to replace with gamma. Okay. You know, just to make things a bit easier, because then if we don't do that, then this becomes much more of a pain to evaluate. Okay. So if we do that, then we get gamma. So that entire first expression just turns into gamma minus u phi at xl, where in this case we replace this with phi c plus phi l divided by 2. Okay. Minus k d phi dx at xl, where this one we're going to replace with our slope. So this can be phi sub c minus phi sub l divided by delta x, okay, is equal to q at xc delta x, okay. And then if you work through the algebra, you get the expression that that was mentioned earlier. Yeah, qxc. Yeah, that was mentioned earlier. We have just xc and xl, or phi sub c and phi sub l, and the gammas on the right hand side. Okay. Okay. So that was just kind of a really quick recap of what we did last time. So then now let's kind of see this all kind of put together in an example. Okay. Okay. So let's write an example. So let's say in our example problem, we have this problem. So we have 5 du dx minus 8 d squared phi dx squared is equal to 3x. Okay. And our domain for this case is going to be 0 is less than or equal to x is less than or equal to 1. Okay. And then our boundary conditions are going to be this. So on the left side, we have a Dirichlet boundary condition. So we have a phi at 0 is equal to 10. Okay. And then on the right-hand side, we're going to have a Neumann condition. So on the right-hand side, we're basically saying that the total flux for this equation is going to be equal to something. Okay. So we have the flux at x is equal to 1. So we know this is going to be on the right-hand side of the equation. This is going to be 3. Okay. So on the right-hand side of the equation, we have a flux of 3 on that side. Okay. So we want to solve for a finite volume solution. Okay, on the following grid. So we have we're going to have 4 cells. Okay. Okay, so we have phi 1, phi 2, phi 3, and phi 4. Okay. Okay. And we want to basically come up with the 4 equations that will solve this problem. Okay. Right. 1 for each cell. So just like as we always did. Okay. Okay. Any questions on the problem setup?
Is it 3 cells?
It's 4. So I basically drew the cell centers here. So the cells look like this basically.
Got it.
Yeah.
So for this example, we're not dealing with Newman anymore. We're dealing with a flux.
Yeah. Yeah.
Okay.
Yeah. So the basically all Neumann conditions now are going to be turned into flux boundary conditions, just because they make things a lot easier to work with. Yeah. Oh yeah. Yeah. Delta x is 0.25. That's correct. Yeah. Thank you. Okay. So then let's write out our parameter value. So we have u. In this case, our u is the coefficient in front of our convective term. So our u is equal to 5. Okay. Our k is the coefficient in front here, where we have the negative right here already, so we don't need to add a negative. So our k is just going to be 8. Okay. And then our q of x is this function of x on the right-hand side. Okay. So our q of x is just going to be 3x right there. Okay. Okay. So first, let's start with our interior cells, because since we know how to write those equations. Oh my God. Okay. So we have 2 interior cells in this case. So we have cells 2 and we have cells 3. Okay. Okay. So let's use the equation that we had before. Okay. So if we basically plug in all the values for our parameters, then we get this this recurrence relation for the interior cells. We have minus 34.5 times phi sub L plus 64 phi sub C minus 29.5 phi sub R is equal to 3/4xc. Okay. So basically, what I did was I plugged in the values of u, k, and delta x into our formula that we did kind of at the beginning, and I came up with these numbers here. So basically, all we have to do is apply this for cells 2 and 3, and then we can get those two equations there. Okay. Anyone still need some time to write this before I turn the page? Okay. Okay, so then this gives us our equations for cell 2. Okay, so for cell 2, we have a minus 34.5 multiplied by our neighbor on the left. So the neighbor on the left of phi 2 is going to be phi 1. Okay, plus 64 phi sub c, where phi sub c is its own value. So this is going to be 64 times phi 2. Okay. And then we're going to subtract 29.5 times the neighbor that's on the right. So the neighbor that's on the right of phi 2 is going to be phi sub 3. Okay. Okay. And then we're going to multiply by 3/4 times xc at 2. So that's going to be x2. Okay. Then next, let's do our equation for cell 3. So it's going to be the same coefficients, but everything's going to be shifted up by 1. Okay. So there's two out of our 4 equations already. Okay. And these are again for the interior cells. Or in other words, the ones that don't border the boundary. Okay. Okay. So the next one that we'll do is cell 1, which is going to be the one that borders the Dirichlet condition. Okay. So just like we, which is kind of good practice for problems with convection and diffusion, let's start with the integral expression.
Professor, is a Dirichlet boundary condition always going to be on the left, like where 1 starts?
Yeah, that's a good question. So so that's not always the case. So the Dirichlet condition could be on the right, so it could be on the last cell. But for this example, I wanted to make it kind of consistent with kind of the derivation that we did. But if you have a Dirichlet condition that's on the right, and you would do that for cell. In this case, it would be cell 4. So that's why it's good practice to go from kind of the integral expression, so you know what to do if you have a Dirichlet condition on the right. Yeah, I'll highlight it as we kind of go through the as we get the equation for it. Okay. Okay. So then if we write out, basically kind of right after we've evaluated our integral for the 1D case, we get this. Okay. To get u times phi, I'm just going to abbreviate. So phi sub r, phi sub little r is going to be the face value on the right side of the cell. Okay. Minus k d phi dx at r. Okay. Minus u phi sub L minus k d phi dx at L is equal to q at xc delta x. Okay. So let me draw the geometry right here. So I'm using the same convention as I did before, where I use lowercase letters to denote solution values at the at the interface between two cells. So that's what this phi sub little r right here is. So that phi sub little r, that's the solution value at the interface between phi1 and its right neighbor. So the right neighbor in this case will be phi sub 2. Okay. And then in this case, let me draw this. Okay. In this case, we don't have a left neighbor because the left is going to be on the Dirichlet condition. Okay. So in this case, since we have a neighbor on the right, this will remain unchanged. Okay. So we're going to evaluate that kind of as we did for the interior cells because we have our neighbor 2 that's on the right. Okay. While this guy, we're going to replace it with an expression with the Dirichlet boundary condition. Okay. Okay. All right. Any questions on this before I turn the page? Okay. Okay, so let's go ahead and fill in those quantities. So first, let's do the first bracket, which is for the right. Okay. So first, we're going to have u times the linear approximation of phi little r. So the approximation for phi little r is going to be phi big R plus phi sub c, all divided by 2, okay, minus k, phi big R minus phi sub c, all divided by delta x. Okay. So that's unchanged. So this is the same as if we had an interior cell because we do have a neighbor on the right. But what's going to change is the one for the left because we have that Dirichlet condition. Okay. So we have u phi naught, which is our Dirichlet boundary condition, because that's the solution value that's on the left border of the cell. Okay. So we know that already. Okay. And then from this, we're going to subtract k times phi sub c, which is our own value, minus phi sub naught, which is our Dirichlet boundary condition, divided by delta x divided by 2. Okay. And this is going to be equal to 3xc times delta x. Okay. Where I plugged in for q as well. So then if we simplify this and we basically move everything that's known to the right-hand side, okay. So all the known quantities are this ones right here. So basically anything with phi naught, basically because we know the value kind of before before we do anything. Okay. And we're going to end up with the same expression that we did, that we went over like 20 minutes ago. Okay. So we have u divided by 2 plus 3k all over delta x, okay, times phi sub c plus u over 2 minus k over delta x, phi sub r is equal to 3xc delta x plus u phi naught plus 2k phi naught all over delta x. Okay. All right. And again, remember, be careful of the signs right here. Okay. All right. So then we plug in all those values. Then we get a formula for phi1. Okay. So we have 98.5 times phi1 minus 29.5 phi 2 is equal to 3 over 4 x1 plus 30, which results from this, plus 640, which results from that. Okay. Okay.
I know this might be simple math, but how'd you get 3K?
Yeah, so the 3K comes from, we get 1K from this, right? And then we get another 2K because we have a delta X over 2 here. So this 2 comes up to the numerator here, and we get another K from 2K from this right here. Mm-hmm.
Oh, okay. Cool.
Mm-hmm. Yeah. Any more questions on this result? Okay. So that's the Dirichlet condition on the left. So now let's do the flux condition on the right. Okay. So the flux condition on the right, basically we're going to replace an entire kind of bracketed term with the flux. Okay. So let's do the same starting point as we did for the Dirichlet boundary conditions. So we have u phi sub little r minus k times d phi dx at little r, okay, minus u phi at little l minus k d phi dx at little l, okay. This is equal to q at xc times delta x, okay. So in the case where we have a flux boundary condition on the right, what we're going to do is we're going to replace this entire term, kind of just like we said before, with our flux. Okay. All right. Right. So in this case, our flux we'll say it's gamma, just to keep things general. Okay. So we have gamma minus everything else here. We're going to keep the same. So we're going to do u times phi sub little l. So to get phi sub little l, we're going to get phi sub c plus phi sub big L, all divided by 2, minus k d phi dx at little l. So this is going to be phi sub c minus phi sub l, all divided by delta x. Okay. All this is equal to q at xc delta x. Okay. Right, so in the end, you get minus u over 2 minus k over delta x times phi sub l plus minus u over 2, plus k over delta x phi sub c. In this case is equal to 3 over 4 times xc times minus gamma. Okay, where I plugged in for phi that xc. Okay. Right. Okay. So then what we can do here is we can basically plug in, and then we can get our equation for cell number 4, which is the one on the right side. Okay. All right. Okay. Am I good to turn the page? Okay. All right, so finally we can plug in those numbers, and then what we get is minus 34.5 times phi 3, because the left neighbor for cell 4 is going to be 3, okay, plus 29.5 times our self, which is phi 4, okay, is equal to 3 over 4 times x4, that's our source term, minus our Neumann condition, which is just 3. Okay. And so that's our equation for cell 4. So combined with our equation for cell 1 and cell 2 and cell 3, that's basically this problem. Okay. So if we put this in matrix form, we can basically solve it kind of like as we did kind of before. All right, any questions on this example? Okay. So for this example, I wrote a MATLAB script, kind of in the same vein as we did before, but kind of since we're a little bit short on time, I think probably I'll save that for after the midterm, because I want to talk about one other thing, which I think will be kind of perfect for the last 15 minutes, and that's this idea of upwinding. Okay. So if you remember when we did convection with finite differences, we ran into this issue where we can get unstable solutions if we use central difference. Okay. So the same thing can happen if you use finite volumes. So just because you change from finite difference to finite volumes, you don't escape those problems. But for this case, it was a little bit more subtle. So let me kind of illustrate kind of what we saw. Okay. So let's say that we have a line right here. Okay. Let me highlight some self-centered values. So let's say that we have phi sub c. Okay. And here's its cell. And then to the the neighboring cells have values phi sub big L and phi sub big R. So if you remember just from the last example, when we integrate the convection term, what ends up happening is we need the solution values here at these cell boundaries. Okay. So from the last example, we call this phi sub little l. We call this phi sub big R. Okay. And then to approximate these, what we did was we just did a simple average. Okay. So in the end, let me just kind of erase what's up here, just so it's all on one board. So in the end, if you did our simple average, what you got was phi sub little l was equal to phi sub big L plus phi sub c divided by 2. Okay. And then phi sub little r, this is going to be phi sub big R plus phi sub c, all divided by 2. Okay. So that was the expression that we used for the simple average, which we used in the previous example. Okay. But this scheme right here, by using just a simple average, this is kind of the same thing as when we use central difference in finite differences. Okay. So for finite volumes, we don't call it a central difference because we're not taking the difference of anything. But basically, we call this kind of the same thing. So instead of a central difference, we call this a central. I just call it kind of a more general central scheme. Okay. where we say that, you know, whatever we need on the face is just going to be just the perfect average between whatever is bordering it on the left and the right. But just like we saw in finite differences, if you use a central scheme for this convection term, you could get an unstable solution if your Peclet number was too high. Okay. Right. So if you remember from before, our Peclet number was given by this. Okay, so we have U delta X all over K. Okay. So if you remember from when we did finite differences, we had to check. So if Peclet was greater than 2, then we have an unstable solution. Okay. So the same thing can happen in finite volume. So you can compute the Peclet number exactly the same way. So you take your convection velocity multiplied by our grid spacing divided by delta divided by K. And if that's over 2, then you still get an unstable solution with finite volumes. So if you remember from finite differences, what we did to fix this was we used backward difference, which was a form of upwinding. Okay. Okay. So an analogous procedure also works for finite volumes. It just works a little bit differently. Okay. So let me draw kind of an example case. So let's say that we have a grid like this. Okay. Okay. So there's our cells. Okay. And then let's say in this case, we have a convection velocity that goes from left to right. Okay. Okay. And if you remember kind of the terminology that we used back when we did convection for finite differences, what we can say is that if the convection velocity goes from left to right, then the things that come from the left are upstream. And that applies for this particular case. So if the convection velocity were negative and it went from right to left, then the upstream direction would be on the right. But in this case, since we have a positive convection velocity, our upstream it goes from is on the left side. Okay. And so what we can do, just strictly for the convection terms, is that instead of doing a central scheme for these face values here, what we can do is instead, what we can use is whatever is upstream of that boundary. Okay. Right. So in this case, we have two face values. We have phi sub little l, which is this guy right here. Okay. And then we have phi sub little r, which is this one right here. Okay. So before, remember what we did is we simply just took the average of the two of whatever was neighboring it. So we said phi sub little l was phi sub big L plus phi sub c divided by 2. But for an upwinding case, since we know the upstream directions from the left, we can basically just take whatever neighbor is on the left in this case. Okay? So for phi sub little l, it borders between phi sub big L on the phi sub big L is on its left, and phi sub c is on its right. So the one that's upstream of this is going to be phi sub big L. Okay, so let's use that. Okay. And then for phi sub little r, we want its neighbor that's on the left side, the upstream side. So in this case, its neighbor on the upstream side is going to be phi sub c. Okay. And then we're going to use this in our finite volume equation instead of the average of what we did before. And then we'll get a slightly different equation for our finite volume equation. Okay. All right. Any questions on this before I turn the page?
So upstream is to the left?
Yeah. Upstream in this case is to the left because our velocity goes from left to right. Okay. So let's see how this looks like in practice then. Okay. So let's start with the same integral expression that we do for the boundary conditions, and then I'll see how the upwinding affects this. Okay. So we have a u. So first we have terms on the right side. So we have u. Sorry. Right. Phi sub little r minus k d phi dx at little r, okay, minus u phi at little l minus k d phi dx at little l, okay, is equal to q at xc delta x, okay. All right, so what we're going to do is we're going to change how we evaluate these convection terms such that they use the upwinding scheme that we did before. Okay. For the diffusion terms, we're just going to keep them exactly the same because diffusion we have no issues with stability, so we can just use our usual scheme from before. Okay, so let's plug in our values from before. So for phi sub little r, we know that we're going to use the upstream value, which in this case can be phi sub c. Okay. Okay. Minus k. We know that our diffusion term is going to be the same. So this is going to be phi sub big R minus phi sub c, all divided by delta x. Okay. Minus u times phi sub little l, where again, in this case, we're going to use our upstream value. So that's going to be phi sub big L, okay, minus k times our diffusion term, which stays the same. Okay. And then our source term stays the same. Okay. So remember, this is very similar to the equations we had before, but our convection terms are different. So the terms that I've circled, we've replaced those with just the upstream value. Okay. And then if you work through the algebra and then kind of rearrange the terms, then you get the following expression. So you get minus u times minus k delta x times phi sub L plus u plus 2k all over delta x times phi sub c plus minus k over delta x phi sub r, okay, and this is equal to q at xc delta x. Okay. So you can see by applying the upwinding scheme where we weight the convection term on the upstream direction, we end up with a slightly different equation for our interior cells. Okay? So you can see that phi sub L and phi sub C, those equations have kind of more weighting for the convection velocity, but phi sub R, because it's in the downstream side, it has no contributions from the convection. Okay. All right, any final questions on this? Okay. So Wednesday we're going to have the midterm. So I won't again, I won't open a Zoom meeting, but I'll post the exam basically at 5:30 sharp on Wednesday, so that you'll be able to download it there and work on it. So again, you know, you don't have to print it out. Although I put it in a form where you can print it out and kind of work on it just as normal. But if you want to work on it on line paper and scan it, that's okay with me too. Okay? So if you have questions on the exam, definitely email me, and I'll try to be as available as I can during that time. Okay? So I guess the next time I will see you guys is a week from today. So you know, good luck with the exam, and then I'll see you guys for the next lecture on Monday. All right. See you, everybody. So if you have any questions, I'll stay on for another 5 minutes, but then I have another lecture right after this, so I can't stick around for too long.
Is everything that we just went over today going to be part of the midterm, or is it mainly just going to be just homework 5 and 4?
Yeah, just homework 5 and 4 is going to be on the midterm. So what we're doing now, it's not going to be you're not going to be tested on it at all, actually. So because this midterm is going to be the last exam, so we're going to have one more homework after the midterm that'll cover this stuff. But this is mostly for the people who are using finite volumes for their final project. So for the grad students, you're kind of forced to do it. But if you want to do the final project with finite volumes, then you'll use basically everything that we've been covering.
Okay, thank you.
I got a question on the homework.
Sure.
Is it going to be uploaded today or tomorrow?
The solutions?
Yeah.
Yeah, so it'll be uploaded probably a little bit after 8:30 because that's when I'm done lecturing my next class. But I'll post it as soon as I can. Yeah.
Okay. Thank you.
Thanks, Professor.
Yeah, thank you too. Okay, so there's no more questions. I'm going to sign off for now, and then this lecture will be posted as soon as I can process it. So probably tomorrow morning. Okay. All right. See you, everybody.